Hi, everyone. Welcome. It's our last lecture before spring break. Oh, the holy? Akshay, help me out. Is it holy?
Yes, it is holy. I think it's technically in US time, it's technically tomorrow, but probably it is holy for people in India.
How cool. It is definitely a festive time, among the reasons why we're coming up on spring break. Holy starts in 30 minutes. All right. Awesome. Well, we'll let folks continue to, or I'll start with a set of announcements. I'm going to close the chat real quick, just so folks can see this announcement that I'm dropping in the chat. So hi, everyone. Amir is back with us today to do a really fun lecture on Grover's algorithm, which you've heard a little bit more, or you've heard a little bit about, and we'll learn significantly more about this week between lecture and lab. I hope you had a wonderful week. A few announcements before Amir gets started. These ones are important, so please listen and check out what I've dropped in the chat. There won't be a standard homework assignment this week. Instead, because believe it or not, we're coming up on the end of the course, we are asking for you to submit your name exactly how you would like it printed on your certificate for this course, so we can start preparing those certificates to celebrate all you've learned and all you've accomplished over this last year. As a reminder, to earn a certificate, you have to have a passing grade in the course. They'll be determined based on pass fail as detailed course handbook. So check your grade on Canvas, make sure you have a 60% or higher. We will work with you if you're struggling and need to get that grade up. Our goal is to award all of you for the incredible work you've done this year. So that will be your homework assignment. If you're looking for additional practice on Grover's, there'll be plenty that Akshay and the TAs share during lab that you can work on instead. With that, there will be no homework review session on Friday. Again, lots of holidays around the world, so we're going to take it a little bit slower this week. On that note, this is our last lecture before spring break. You also have lab this week, so please, please, please be there. It's a really fun lab. And then we'll be on a 2-week spring break. So no lecture or lab next week or the following week. And we will return on April 18th, again with Amir, to learn about hardware and implementation. So again, a really fun lecture series. But enjoy 2 weeks off. It's a good chance to get caught up on homework assignments. We've extended the deadline on one of our homework assignments in case you want to try again or get a higher grade. So we want you to use this time to either rest or get caught up on assignments and things like that, if that's what you need to do. 2 last announcements. So for spring break, Shay and the TA team have developed a set of cheat sheets on key assignments from this semester. So check those out. Several are already posted on Canvas and more will be coming. So again, a good way to freshen up your memory as we come up on the end of the course. We'll also have a coding practice notebook for those who are still getting comfortable with Qiskit and Python. And then look back to your old lab assignments because Akshay has had incredible optional content in every single week. So practice those if you want to go kind of the extra mile in terms of learning the content. And then just lastly, like I said last week, we have announced our summer programs. So we have a 1-week middle school camp, a 1 to 2 week high school camp, and then a 4-week summer school, be fairly similar to the content covered in this course. So please encourage your friends, your classmates, your family members, your little sister, whoever, to apply for programs. I've dropped the link in the chat and we're reviewing applications on a rolling basis. So the sooner they apply, the better. The hard deadline will be April 16th. Sorry for so many announcements. Please let us know if you have any questions, but otherwise I'll turn it over to Amir to get us started.
Amazing. Thank you so much, Rachel. It's great to be back. And today we're going to be talking about a quantum algorithm. But before we dive into Grover's search algorithm, let's just do a quick recap of what is an algorithm. So the act of computation involves having an input and mapping it to an output using a set of instructions. Now, these instructions are defined or called algorithms sometimes. Specifically, an algorithm is a set of well-defined instructions to perform a computation. And a computation maps an input to a desired output based on some set of laws. Let me quickly change my pen color to black because I think people do prefer it better that way. Amazing. So far, this is a review of what Fran talked about in the past lecture. The quantum algorithm landscapes look something like this. So we have the Deutsch-Jones algorithm, which was the first demonstration of some form of quantum advantage. Namely, in that case, for let's say 2-qubit instance, for a function, we were able to tell if the function returns the same output regardless of the inputs, or if it returns different outputs depending on the input, with only a single inquiry using a quantum computer. Whereas classically, if you want to figure this out, you need to do at least 2 inquiries to see if you get a different output or not. And that was a very early demonstration of some form of quantum advantage proposed before Shor's algorithm in the 80s. But then we get to Shor's algorithm, which is a real impressive quantum speedup or signature quantum advantage. So it offers a super polynomial speedup for factoring using something called the quantum Fourier transform that we briefly discussed in the previous lecture. And the significance of Shor's algorithm is that factoring is perceived to be a hard problem, although not proven classically. And therefore, there are a lot of cryptography protocols based on factoring, based on the assumption that, if I have 2 large numbers, I multiply them, factoring them out is actually difficult. Whereas with Shor's algorithm, a quantum computer can perform the task of factoring efficiently, and therefore it could break all these crypto systems. So that was, in terms of the timeline, the factoring algorithm was introduced in 1994, and that was when quantum computing as a field started gaining traction. Now, the algorithm that we're going to talk about today is the Grover search algorithm, which offers a quadratic speedup for search, specifically searching an unstructured database using a technique called amplitude amplification. Now, we're going to talk in detail about what amplitude amplification means. But the idea here is that, and again, we will go into more detail here, if you're trying to search for an element in an unsorted list or an unsorted database, chances are you might have to look through every single element of that database to find what you're looking for. Therefore, we say that classical search takes O of n in terms of complexity. However, with a quantum computer, it can do that quadratically faster. So instead of looking at all n elements, or let's say n over 2 elements, you can look at square root of n elements. And that's an impressive speed up in and of itself, and it's guaranteed, it's provable. Now, the last set of algorithms, which we're going to talk about actually 4 lectures from now, after our implementation lectures, are near-term algorithms. And specifically with near-term algorithms, we're trying to figure out what can we do with noisy small devices, quantum devices that we have access to today. By noisy, I mean that the qubits aren't perfect. There is a probability of error. And by small scale, I mean anywhere between 50 to 200 qubits. Although the exact number for what constitutes a small scale device is, of course, up for debate. And the idea for the near-term algorithms is that we take advantage of the quantum circuits that we have available and compute them with the classical computing resources that we have available, such as our CPU or GPUs, and we try to accomplish some quantum advantage that way. Okay, that being said, let's dive into Grover's algorithm. So the problem that we're trying to solve is searching, but we're assuming that there's no data structure. So our list or the database that we're searching through is not sorted in any way. And why do we care? Well, searching is everywhere. First of all, if you're Googling something, for example, you're searching a massive database of online web pages. But also, every time you look for something in your computer, chances are your computer is doing a search. Or if you're using Control Find or Control F on a Word document, you're searching through the document. So searching is really everywhere. Now, the method that we use is using the quantum circuits that we've discussed so far. Namely, we start with some quantum states, we apply some gates, and finally, we measure the output state. And the idea is that if we have an efficient and correct algorithm, by the time we measure the output state, we're going to get the correct answer with very high probability. Okay, so let's talk about Grover search specifically now. Yeah, the goal is to search an unsorted list of length large n elements for a specific element. And the assumption that we're making is that we already know what we're looking for. We just don't know where it is. So we're trying to find the location of a target in a list. We know exactly what we're looking for. For example, if I go grocery shopping and I'm looking for an apple in the grocery store, I know that I'm looking for an apple somewhere. I just have to figure out exactly where it is so I can go pick it up. So that's the premise of the problem that we're tackling. So as I mentioned earlier, classical search algorithm takes O of n, or where n is the number of elements that we're trying to search for, whereas quantum search takes O of square root of n. Now this big O notation is what we discussed in previous lectures. It's just an asymptotic notation, meaning that worst case, I have to look at something that is of order of large n elements. Now, let's see the difference with a concrete example. Let's say that I have a list of size 1 million elements, and I'm trying to search for a specific element in this list. Using a classical search algorithm, chances are we would have to make, of order of 1 million inquiries. Whereas using a quantum search algorithm, this number gets reduced to only 1,000 queries. And that is a significant difference. So at a high level, why can a quantum algorithm outperform the good old classical search that we know? Well, this goes back to the quantum resources that are at our disposal when we perform quantum computing. Namely, we start by putting our overall quantum state in a superposition of all possible solutions. Then we use entanglement and quantum interference as resources, in this case, to decrease the probability, or specifically the probability amplitude of getting the incorrect answer, and increase the probability or the probability amplitude of getting the correct answer. We're going to see how that works in a few slides, but this is just to give you guys an overall picture of what is happening in Grover's search algorithm, but also these resources do extend beyond just Grover and to any quantum algorithm, really. So let's look at an example. And the example that we like to think about is Where's Waldo? So Where's Waldo is this kind of a puzzle-like exercise, in a sense, where we're looking for this guy Waldo in a very big picture that has a bunch of different characters. So we know we know Waldo. We know what Waldo looks like. Specifically, Walt is tall, skinny. He's a man. He wears blue jeans. Has a red and white striped shirt. Wears glasses, and has a cane and smiles. So we know what Waldo looks like, which is this guy. And we also know what Waldo doesn't look like, namely all these other characters. So these characters are not Waldo. And we're trying to find Waldo in this big picture. So if we were to find Waldo using a classical approach in this picture, we would go to every single character in the picture. We would look at it and be like, okay, are you Waldo? This guy's not Waldo. Next one, are you Waldo? This guy's not Waldo. And we'll also go to the dog. Are you Waldo? Nope, he's not Waldo either. So we would have to go basically, character by character, take a look and, either confirm that, the character is Waldo or that he or she is not Waldo, and then move on to the next one. And this is not very efficient. And the efficient that we say here is just that it just means that it can take forever if, we have a very large picture. In fact, that's why, whereas Waldo is a challenging exercise because you kind of have to almost look through the whole picture and until you find Waldo. Now, what if we could use Grover's search algorithm or, some search algorithm like Grover's on this picture to find Waldo? Well, so we make use of, something called an oracle function, which we discussed in the previous lecture, but an oracle function is a function that basically knows, who Waldo is. So for example, we can think of it as this magic genie that, when we get to every character, we can ask the genie, hey, genie, is this character Waldo? And, the genie will tell you either yes or no instantaneously. So that's the premise of an oracle. Now, using this magic genie combined with quantum resources, that again, we'll see how, we can actually do this process much more efficiently. So we have this oracle function. We do one iteration of Grover's search. And what happens is that in this picture, the contrast of all the other characters go down a bit and the contrast of, or the brightness of Waldo goes up. So now you can see that this area is getting a little bit brighter than the rest of the picture, but it's not immediate, right? So if you just look at this picture, very quickly, you might still not be able to find where Waldo is with just a single look without actually looking through. So let's apply this process more times. So now when I applied another times, again, the part where Waldo is becomes a little bit brighter and everything else becomes a little dimmer. We can still do better. So let's apply it one more time. Okay, we can see that things become brighter. Now, all of a sudden, if I look at this picture, I'm almost able to find where Waldo is immediately, which is somewhere here. And, one last time, we can see that again, Waldo is very bright and the rest of the picture is very dim. And, to compare with where we started, where everything was at the same brightness, we can see a difference because again, when we look at this picture immediately, we can't identify where Waldo is. Now, of course, this is an example, but in a sense, what Grover's search algorithm does is exactly what we described here. By applying these quantum iterations of the algorithm, we increase the brightness of the correct answer and decrease the brightness of everything else, such that when we finally measure the quantum circuit, we're able to see, or we're able to measure the correct answer with high probability. So again, what makes Grover's quantum? So how are we utilizing these quantum resources in Grover's algorithm specifically? Well, to give you guys a reminder from the beginning of this semester, I believe, lectures 1, 2, and 3, where we talked about quantum mechanics, qubits behave as both particles and waves. That was a concept of wave-particle duality that we discussed earlier in the semester. Now, what we do is that we can put all these choices and each of these characters, each of these spots containing Waldo into a superposition and then utilize the wave-like behavior of qubits to make things interfere such that the amplitude or the brightness of where Waldo is increases and the amplitude or the brightness of everything else decreases in a sense. So again, this is the concept of constructive and destructive interference that we've discussed earlier. So for example, for the characters that are not Waldo, we want to somehow create interference or an interference pattern such that if you start from this probability, equal probability amplitudes, their final probability amplitudes decrease. So let me do this. Whereas for Waldo, we want the probability amplitudes to increase as we apply more and more iterations. So, and again, the takeaway message here is that incorrect solutions get destructively interfered, and correct solutions experience constructive interference. Now, of course, later on in the lecture, we will plot the amplitude of these waves. And again, the way that we do it is using these probability amplitude plots. So let's say the green in the plot here is the correct answer, and everything else is an incorrect answer. We start by all the answers having the same amplitude, and as we perform the iterations of our algorithm, we do them such that all the incorrect answers destructively interfere and go down in amplitude, and the correct answer goes up in amplitude. Okay, so let's see how this is done. And again, we're gonna, the way that we're gonna approach this lecture is that first we're going to explain how Grover's works conceptually without showing you guys the math or a proof of the runtime. And then in the second part of the lecture, we'll talk about why is it that actually we say that Grover's algorithm runs in O of square root of n, or takes time of order of square root of n instead of order of n, where n is a number of elements in the list. So the steps are fairly straightforward. The first step is that we start with an equal superposition of all possible solutions. And then the second step is that we use this amplitude amplification technique, which is something that I conceptually described so far, but we will see in more detail. And then the final step of the algorithm is that we measure the outcome of the quantum circuit, and with high probability, we're going to get the correct answer. Okay, so specifically, when we put things in equal superposition, we start by assigning equal probability to every cell being the correct answer. When we perform amplitude amplification, we use quantum interference to transform the superposition such that the correct cell has a significantly higher probability in this superposition. And finally, we measure the circuit. And once we measure the state with high probability, the result is the right cell. And in fact, there are modifications to the algorithm that I'm going to describe for you today, such that we can get the correct answer, not with just high probability, but with 100% probability. The circuit for Grover's algorithm looks something like this. So, step one is where we put everything in an equal superposition, and that is just by applying Hadamard's to every single qubit that we have. That creates an equal superposition of all possible states. Then step two involves applying two different unitary operations, which we will describe, but this oracle operation, which again, we will visit, and then an operation that essentially reverts everything with respect to the mean. And we will repeat the combination of these two operations for O of square root of n times. So the combination of these two operations, these two unitary operations, is usually called the Grover iteration. And what I'm claiming is that we need to do O of square root of n Grover iterations for the amplitude amplification part, which is step two. And then we finally measure the circuit. And chances are with high probability, we're going to get the correct answer popping out. Okay, so let's take it step by step. So we start by assigning equal probability to every cell being the right answer, which is an equal superposition. Again, as I mentioned earlier, we can create this equal superposition by applying a Hadamard gate to each qubit. Now, the probability amplitude that we have for each state is going to be 1 divided by square root of n. And again, if you remember, this probability amplitude corresponds to a probability actually of the probability amplitude squared, which is 1 divided by n, and n is a total number of elements that we're trying to measure over, or that we're trying to search over rather. So that is the difference in probability amplitude and probability. Again, specifically, let me just draw another example here. So if I had psi, and this is a generic qubit state, is equal to alpha, let me fix this. If it's alpha times the 0 state plus beta times the 1 state, this alpha and beta were probability amplitudes. And the corresponding probabilities of measuring 0 and 1 were alpha squared, rather amplitude of alpha squared, absolute value of alpha squared, and absolute value of beta squared. So here we start by putting everything in, just to recap, in an equal superposition of all possible states, meaning that the probability amplitude of each of our states is going to be 1 divided by square root of n. Now, if I were to measure, I'm going to get the correct answer at this point with probability 1 divided by n. And we're assuming that the green bar that I have here represents the probability amplitude of the correct element, the element that I'm looking for. And everything else corresponds to probability, or the red bars correspond to probability amplitude of everything that I'm not looking for. Okay, next, so this is the step 2 of the algorithm. We use quantum interference to transform our superposition so the correct cell has a significantly higher probability of being measured. And for that, we apply, this thing called an oracle operator. And all the oracle operator does is that it flips the sign of the amplitude of the correct state. So it went from everything being at an amplitude 1 divided by square root of n to now the correct answer being at amplitude minus 1 divided by square root of n. So what we did is that we flipped this amplitude. So this went, from up here to down here. Now, how that works exactly, we will discuss. But the idea here is that since I'm in a quantum superposition, if I only apply, a single oracle operator to the superposition, it'll act on every single element. And we will talk about the construction of the oracle in a bit. But the idea is that the oracle does not flip the amplitude, and by flipping, I mean just adding a negative sign in front, does not do anything to the incorrect answers and just adds a negative sign in front of the correct answer, or the amplitude of the correct answer, the element that we're looking for, such that it goes down. Now, the next part here is where we invert the amplitudes with respect to the mean. So now, after the second, or after the oracle operator, if I calculate the mean of my operators, or sorry, not my operators, but the amplitudes that I have, it's going to be a little below 1 divided by square root of n. Because, okay, all these amplitudes are at 1 divided by square root of n. But now, of course, we have this one amplitude that's minus 1 divided by square root of n. So that means that the mean is a little bit lower. Now, if I revert everything with respect to the mean, all these amplitudes, all the red amplitudes are going to go down, whereas the green amplitude will shoot up because everything is just being reverted with respect to this line. So now what happens if I were to draw this, the whole second step, the Grover iteration in one slide, we start with everything being in an equal superposition. We apply the oracle operator, which flips the sign of the amplitude of the correct cell that we're looking for. And then after we apply, the second operator, which inverts everything with respect to the mean, we see that the probability of the correct answer went up, whereas everything else went down. And here at every step, every time we do this, we amplify the amplitude of the target cell. And the target cell is the cell that we're looking for. And then after of order of square root of n iterations, the target amplitude is near optimal, meaning near 1 or at 1, which means 100% probability of measuring it if we actually measure the state. And these class of quantum algorithms are referred to as amplitude amplification. Because in a sense, what we're doing is that, again, we're amplifying, we're increasing the amplitude of the correct answer while decreasing or destructively interfering the amplitude of all other possibilities where are not the correct outcome that we're looking for. And finally, after we perform O of square root of n Grover iterations, the probability distribution that we have, or rather the amplitude probability amplitude distribution that we have, looks something like this. And then once we measure this circuit, chances are with high probability we're going to get the green bar, or rather the cell that points to the correct answer that we're looking for. So the last part of Grover's search algorithm involves measuring the right cell. So if we were to visit or revisit the Where's Waldo example that we have, when we have the picture, the way that we do that basically corresponds to every single person in the picture being Waldo with the same probability if I just take one look at the picture. Now, again, we do this amplitude amplification step, or the Grover step, where we use the oracle to flip the amplitude of the green cell, which is the correct cell that we're looking for, and then we revert everything with respect to the mean, which shoots up the green cell above the other red cells, or the other cells that we have. So after one iteration of Grover, the green is a little bit higher than the red, but not significantly. So if I take a quick look at the picture, okay, I know where Waldo is by now, and what I can see is that, okay, the Waldo does have, it's a little bit brighter, but that's not something that I can tell if I just take a quick peek at this for the first time. Whereas, after we repeat the Grover iterations more and more, Waldo starts becoming brighter again as the probability amplitude of the green cell, or the target that we have, increases. So Waldo becomes brighter. One more time, Waldo becomes brighter. Again, Waldo becomes brighter as I apply this more. And finally, this picture is very clear. If I just take a quick look at this picture, Waldo's the first thing I see. And that corresponds to essentially the steps of the algorithm and making a quick measurement. Now, Grover's search algorithm has many applications. Of course, it speeds up database search. As we discussed, if you're looking for a certain element and you know what the element is, you can find which cell contains that element. But it can also speed up optimal scheduling. So for example, if you're trying to schedule flights in a way such that you're making optimal use of your aircrafts and your airport landing spaces, it could also help with that. It speeds up mean and median estimations. Now, of course, this has a lot of applications when it comes to data processing, image processing, things like that. And also it speeds up element counting. So if you're trying to find how many of a specific element you have of your list, it also helps with that. Now, of course, there are some open research questions also when it comes to Grover search algorithm. Specifically, and this is an assumption that we made early on, is how to efficiently load a classical database to a quantum computer. Now, we assume that we start with some quantum data set that we can search over. We can put in an equal superposition and kind of deal with it that way. But that's not necessarily the case always. In fact, all the databases that we have available today are classical databases. Now, of course, you can make the argument that, hey, we can just copy the database over from our classical computer, to quantum computer, kind of like write each element by hand and then do Grover search. But of course, at that point, copying over, writing down every element by hand will take of order of the number of elements in time. So if you have n elements and you're just copying them over, writing them over, it's going to take O of n, which is the runtime for the normal search algorithm. So that way you're not actually gaining any benefits using Grover search. So in order for Grover search to actually give you a meaningful speed up with the current classical databases that we have, we need to come up with a way to efficiently load our quantum data into our classical data into our quantum computer or into quantum data. And of course, that brings us to the idea, the proposal rather, for a QRAM, which is a quantum RAM, where there's some efficient way to, again, access a classical database and convert it to a quantum database without actually painstakingly writing down every single element. And this is an active area of research right now. There are no, I guess, definite answers for what is the best way to do this. We just know that there's a need for this. And it's not just for Grover search, but also for a lot of quantum machine learning algorithms that assume the existence of a quantum RAM, a way to load classical data efficiently into a quantum computer. But of course, people are still working on finding the best way to do that. Another state-of-the-art research question for Grover's algorithm is, what is a good way for constructing this oracle operator that we talked about? So again, the oracle operator is an operator that we apply to every single qubit, and it tells us, if we have the correct answer, it will flip the amplitude of that element of the superposition without changing anything else. And that is with one try, of course. And finally, what is the relationship between Grover search algorithm and other quantum algorithms? Is there a way to unify, in a sense, what makes quantum algorithms faster than classical algorithms? Because it has been shown that Grover's algorithm is actually optimal for search. So there's no other quantum, classical, or any other algorithm that can do search faster than Grover search. But now the question is, how is there a way to kind of tie Grover's back, or its amplitude amplification back to other algorithms? Because we know that other algorithms do take advantage of amplitude amplification. Of course, but it's still not clear as to what is the nature of the speed up, and that's an active area of research. So with that, let's take a 10-minute break, and then we're going to dive in. Then we'll answer plenty of questions, and then we'll dive into the different parts of we'll revisit the Grover algorithm, and we'll dive into different parts of it with a little bit more.
Amir, can you put the time that will return on the slide?
Yes, and I will write the time in ESC. So we will return at let's say 49 p.m. Eastern Standard Time.
I'll never catch him while I'm this small. Why, curious butterflies.
You mean bread and butterflies?
Oh, yes, of course. Hmm?
Okay, I think it's about time to start again. Before we dive into the rest of the lecture material, let's maybe answer some questions. So Rachel, could you please? You're on mute, by the way.
When it's for a few friends, really bad when it's for 1,000 people. Anyways, let's start with folks were wondering, how does this work when you're working with a multiple element search?
Yeah, so that is something that I didn't discuss for the sake of simplicity, but actually if you have multiple of the same element in the list, the algorithm works the same way. And what it does is that it amplifies the probability of all the correct answers. And at the end, if you measure, you're going to get one of those indices with some probability depending on how many different elements you're looking for. So if you're looking for, let's say, if they're like 2 copies of the elements that you're looking for, you're going to get each of those cell indices with 1/2 probability.
Cool. Okay, so we got a lot of questions, unsurprisingly, about oracles, which we talked about a little bit in lab last week, but are definitely a confusing topic. So folks asked for more clarification in general on the oracle. They asked, how do we get the oracle function? Do they write it? And then how does the oracle determine the correct element?
Yeah, so we are going to see explicitly what the oracle looks like in a couple of slides. Specifically, we're going to define a function that does that job. The one takeaway message that I think we need to have about the oracle going forward to the rest of the lecture is that it somehow knows what the correct answer is, not where it is at. And it's kind of like, when we look for Waldo, right? We know what Waldo looks like. We just don't know where is Waldo at. And we're trying to find where is Waldo at. So same thing goes with the oracle. Or the oracle knows, what Waldo is. It can tell, if you feed it the Waldo, it'll instantaneously tell you, okay, this is Waldo. But it doesn't know where Waldo is. And again, the other key point that I want to emphasize is the word instantaneously, meaning that the assumption that we're making here is that the oracle can, decide if something's like the correct answer or not, without any time complexity, in a sense. Just if that's not clear, just the word instantaneous really describes it well.
So springboarding a little bit off of that, asked, like, I thought we weren't to know Waldo is, which you just clarified. Then how do we know which cell to amplify? What's the criteria for identifying his location?
Yeah, so the thing is that before measuring, really, we don't know what cell to amplify, right? Because if we knew what cell to amplify, then we know the answer and we can all go home. The idea is that, since we start with everything in a superposition and we have this quantum parallelism, if we only apply this oracle operator once to everything, it'll act on every single element of the superposition. So with one application of the oracle operator, it acts on every single part of the superposition, every single element of the superposition. Now, what it does is that it flips the probability amplitude, right? But now the thing is that if you actually try to measure the state after the oracle operator, since you're squaring everything, you're not going to see any difference. It's only with that second part of the Grover iteration, the reversion around the mean, that you see a difference. And now here the idea is that if you have a negative element and you're flipping everything with respect to the mean, all of a sudden the difference between the negative value that you have and your mean value, which is a positive value, is going to be much larger, so you end up going up a lot. And again, this we will see this in action more with a bit more math, and not in a scary way, hopefully, but just like, a bit more elaborate. So it should make more sense.
Amir, can I throw you a curveball that just showed up in the chat? Okay, I'm curious to hear how you'll answer this. Ashwin asked, isn't the way that our brain searches for items very similar to this algorithm? Can you help us understand how we might think of it similarly or differently than Grover's?
Yeah, so that's a good question. So of course, I don't know how our brain works internally. If I knew, that would have been a Nobel Prize for me. But I can tell you that, again, going back to the Waldo example, when we're looking for something, we can think of ourselves or our brains as the oracle here. We know what we're looking for. We know, if the character that we're looking at is Waldo or not. And actually, I think this ties back to another question that I saw, is that, so, the way that we do it classically is that, if you're trying to be very rigorous about it, we're going to go look at every single character, and the oracle that's in our head, again, i.e. our brain, is going to be like, okay, this is not Waldo, this is not Waldo, this is not Waldo, this is not Waldo. And we have to repeat this process until we actually see Waldo. Now, I think that ties back to another question that we got, that, okay, if the oracle knows the answer, why do we have to go through the pain of, this quantum algorithm? And the problem here is that, it's true that the oracle does know the answer once it sees the answer, but, if we were to just do it in a brute force way, we'd have to go through every single element of the superposition one by one, apply the oracle and see, to which one does the oracle give a thumbs up. And that will take, O of n, which is the same runtime as a classical algorithm. I mean, effectively, that's classical search that we do normally when we're looking for an element.
Cool. Okay, how about one last one? Someone asked, how many qubits do you need if you have a list of n elements?
Yeah, so that's a good question. Maybe I'll write it down here. So if we have large n elements, we will need, I mean, it's just an idea of like how many, or rather how many bits do we need to represent this number? So we will need small n, which is usually, so large n is saved for the total number in these quantum algorithm conventions, and small n is usually saved for the number of qubits. You will need small n equal to log 2 of large n, and this is rounded up. So, let's look at the easy case. And actually, we'll see this, I'm pretty sure, in the next slide. If we're trying to search over 4 elements, we'll need 2 qubits, which is 4 log 2, to represent these 4 elements. And that's all there is to it. I mean, you can also look at it the other way, right? Like with n elements, with small n, with n qubits. So with small n qubits, we can represent large n, which is the total number of elements, equal to 2 to the power of small n, the number of qubits. And this is something that we've seen before. This is exactly the same argument that we've seen for if we have, small n qubits, how many different states can they be in a superposition of? Same argument.
Cool. How about we stop there and we'll take a few more questions at the end if there's time.
Sounds good. Yeah, and I believe that we should have extra time at the end for questions. Okay, so let's talk more about Grover search algorithm. Specifically, how does the quantum search speed up work? So far I've told you that the runtime is O of square root of, again, large n, where large n is the number of elements, but why is that the case? So before we talk about the general case with large n elements, let's look at the case where we're searching over 4 elements. So in this case, 4 elements, I can represent them with 2 qubits. But even before then, I can write these elements as, I can call the first one 0, 1, 2, and 3. Right? And if you want to represent them with qubits, you can write it as 0, 0, 0, 1, 1, 0, and 1, 1. So this is, what I have down here in parentheses is just a binary representation of what I have up there. Now, the one rule that we want to follow is that these states are orthonormal. And and we've seen the concept of orthonormal many times throughout the course, but just to do a quick review, if I had, let's say, the overlap between I and J, where I and J are 0, 1, 2, 3 in this case, it's going to be 0. So there's going to be no overlap between I and J if I is not equal to J, and it's going to be a 1 if I is equal to J. In other words, the norm of each of these states is 1, meaning the overlap of each state with itself is 1, and the overlap of the state with any of the other states is 0. So that is the assumption that we're making. And again, we've seen this for the 2-qubit case. It does follow that. And in this case, let's say that we're looking for state W, which we call the winner state. That's the element that we're searching for, or rather the index of the element that we're searching for, depending on how you want to look at it. And let's say in this case, this W is equal to state 2. Could be anything really, but I'm just using state 2 as an example here. So we start by assigning equal probability to every state being the correct answer. So I'm going to call this initial state here the S state, and it's just simply so my total number of elements is 4, so I'm going to have 1 divided by square root of 4. Then I'll have 0 plus 1 plus 2 plus 3. So right now we're in equal superposition of everything. And if I measure this state as it is right now, I'm going to get 0, 1, 2, 3, and 4, each with a quarter probability. So if I write probability of 0 is equal to probability of 1 is equal to probability of 2 is equal to probability of 3, and they're all equal to 1/4, which is just this amplitude squared. Now, if we look at the circuit, we get the same thing because we end up with a superposition of 0 plus 1 divided by square root of 2 after we apply the Hadamard to the 0 state on each of the qubits. And once we take the tensor product of this, maybe I'll do it down here. So I have, for the circuit, I have 0 plus 1 divided by square root of 2, tensor producted with 0 plus 1 divided by square root of 2. And here, of course, the factors of 1 divided by square root of 2 will multiply. So I get 1 divided by square root of 4 out there, which of course is 1/2, but I'm just keeping it that way so I can stay consistent with the form that I have above the page. And then I have the tensor product of 0 with 0. The tensor, maybe I can draw this. Yeah, 0 with 0, then 0 with 1. And then this 1 with 0, and this 1 with 1. And of course, these are just the binary representations of 0, 1, 2, and 3. So again, going back to the general idea here, we start with every single state being in an equal superposition. In this case, we have 4 states. And then we can represent it using this graphic, of course. Now, let's just do a quick review of what an outer product is. So we have seen this earlier. An outer product is just a matrix, and we represent it as a ket, and a bra. So this is the ket, this is the bra, and the whole thing is an outer product. And all this is a matrix where the matrix element of for example, the 0, 0 matrix element is 1, and everything else is 0. So in this case, if I have 0 outer producted with 0, that just gives me 1, 0, 0. It's just a matrix, just like that. Or if I have 1 outer producted with 1, again, that's just a matrix where the 1, 1 element is equal to 1, and everything else is equal to 0. 0, 0, 0, 1. Now, of course, I can have more complicated outer products. I'm not just limited to 0 and 1, right? I can have, let's say, the plus state, the outer product of the plus state with itself. And of course, as a review, the plus state is just the equal superposition of 0 plus 1 divided by square root of 2. Now, the way that I like to approach this is that I'm just going to expand the superposition in terms of zeros and ones. So here I have, and I'm going to factor, okay, maybe I'll leave this for now. But I have 0 plus 1 divided by square root of 2, outer producted with, again, 0 plus 1 divided by square root of 2. Now I'm going to factor out these 1 divided by square root of 2 factors. And then I'm going to go and do these outer products one by one. So let's just bring out a 1/2 here. And then, I'm going to have, everything is linear here. So we're going to have the outer product of 0 with 0 plus the outer product of 0 with 1. And here I'm going to have the outer product of 1 with 0. And finally, I'm going to have the outer product of 1 with 1. And then, as I discussed earlier, each of these, like, 0, 0, or 0, 1, each of these tells you, which matrix element is a 1. So I'm going to keep the 1/2 here. I have a 0, 0 element here, which means that my 0, 0 element, I can put a 1 there. I have a 0, 1 element here, which means that I can put a 1 for the 0, 1 element. I have a 1, 0 element and a 1, 1 element. So that's what the matrix looks like. Now, why is this a useful tool? Why is this a useful way of representing a matrix? Well, let me show you why. So if I want to multiply, let's say, let's go back to the 1, 0, 0, 0 matrix, right? If I want to multiply this by the 0 state, which is the 1, 0 vector, I can just do the normal matrix multiplication, right? I get 1 times 1, and then I get 1, 0. So that's just a simple matrix multiplication. But now using this tool, I can use the bracket notation to do it a little bit faster. So I have 0, 0 here. This is an operator or a matrix, and I can apply it to the 0 state here, acting on 0. So now the way that I can write this is I have a 0 ket here, and I can just look at I have a 0 bra acting on a 0 ket, which just gives me the overlap of 0, 0. And what is this value? If you remember, that's just equal to 1. So I end up with the 0 state. So I was able to do this a little bit faster instead of doing the matrix multiplication. This is a useful tool in general, but we are going to see it when we talk about the operators for Grovers. So with that in mind, let's revisit the oracle. So again, for Grover's algorithm, in the second step, which is the amplitude amplification step, we use a black box that gives us an output for a given input for free. So what do I mean by that? Let's say, we have a function, f of x, and this f of x is the oracle. It gives us a 0. It returns a 0 if x is not equal to w, or to write it in text, if x, the input state that we're checking, is not the target state. And it'll give us a 1 if x is equal to w. Or again, to write it in plain English, if x, the state that we inputted, let me make my x a little bit nicer, is the target state. And now I wanna construct an operator, calling it U of, again, W for winner, and this is an Oracle operator that does the following. It takes the state X and maps it to -1 to the power of f of X, of course, multiplied by the X state. So now, if X is the target, again, maybe if X is the target, the value of f of X will be 1. So what I'm going to end up with is that my X state goes to a negative sign in front of X. And now if X is not the target, X doesn't change. Because then if X is not the target, then the value of f of X will be 0, and -1 to the power of 0 is just 1. So that is what the Oracle operator is doing. And the way that I can define it is actually using, again, this outer product notation, using this. So I have the identity minus 2 times the outer product of the winner state with itself. So again, let's look at the example that we had. If W is equal to 2, like we mentioned, we're going to have the identity minus 2 times 2, 2. Okay, so let me write the matrix form for this. And in this case, we're looking at, we're searching over 4 elements, which means that we're going to have a 4x4 matrix. And actually now you can see why I like the outer product better, because as we add an extra qubit, the system size gets twice as large and our matrices just get larger and larger. So here, okay, the identity is going to be 1, 1, 1, 1, all on the diagonals, and everything else is going to be a 0. And I'm going to have 2 times, and this 2 outer producted with 2 matrix is just going to have, it's just going to be a matrix with all the zeros except for the 2, 2 element. So this is the 0, 0 element. This is the 1, 1 element. Now we're going to have a 1 for the 2, 2 element, and then zeros everywhere else. Now, if I were to do the simple subtraction, what I end up with is a 1 on the diagonals everywhere, except for the element, or except for the the matrix entry for the correct answer. So it's going to look like this. And again, the zeros you can just ignore. So everything on the diagonal here, we have 1, 1, and then a -1 for where the 2, 2 element is, and another 1. So that's all there is to it. You can think of all these operators as matrices, and now I just showed you what the matrix looks like for the operation. But in general, I think the main takeaway message really is, this kind of like, this part tells you what the operator does. And again, one way that I like to think about the Oracle is just an all-knowing genie that knows if a cell contains a correct element or not, if the genie is looking at the element. Okay, so let's go back to our example. So if we start from the equal superposition state S, which was just 1 divided by 4, 0 plus 1 plus 2 plus 3. I can write this, actually, I can, in a way, separate the correct answer from everything else. So I can write this as 1 divided by 4, or square root of 4 rather, times the 2 state, plus, then of course there's everything else. 1 divided by 4 times everything else, really. 1 plus 3. Okay, so now if I apply the oracle operator here, which is u of w, and again, I'm gonna write the form, what it looks here, which is the identity minus 2 times w. In this case, I said that w is equal to 2. That's just an assumption we made. It doesn't have to be that way. This is just as an example. Okay, so if I apply the u of w to this S state, I can rewrite that as the identity minus 2 times, again, this matrix element, now acting on basically everything there. 1 divided by square root of 4, 2, plus 1 divided by square root of 4, times 0 plus 1 plus 3. Right, so far I'm just writing the forms for each of this. Now, so now let's go one by one. Let's apply the operator to the 2 state here first. So maybe I'm going to write this as just u of w acting on 2. So what I get is the identity minus 2, and this 2 is just the constant factor, times the 2 state. And this is all acting on the 2 state. Well, so okay, I have an identity acting on it. An identity acting on any state doesn't change the state, so I end up with just a 2 here. And now I have minus 2 times this thing, where the 2 here is the state, and then this outer product of 2 is just the operator. Now, what do I get here? So I told you that the inner product of any of these states with itself is just the same state, or say just 1. So this is just 1, and what I have here is a 2 state minus 2 times the 2 state. So I end up with a minus 2 here. And now, as an example, I'm just going to apply, this operator here to, let's say, the 0 state. And the argument that I'm going to make is that if we don't have the right answer, I expect the operator to behave the same regardless of what that answer is. So I'm going to, again, quickly write this. So I'm going to have the identity to here, acting on 0. The identity acting on the 0 state is just going to give me a 0. And then I have minus 2 times, again, this outer product acting on 0. Now, let's look at this inner product that we have formed over here. So what I mentioned earlier is that if the states aren't the same, the overlap between the 2 states is just 0. So what I end up with here, the overlap between 2 and 0 is just 0. So this whole part essentially is 0. So what I end up with at the end of the day is just, the same state, but with no negative signs. So based on this, if I apply this, going back to what we had up here, when I apply this operator to the S state, the coefficient in front of the correct answer, which in this case is the 2 state over here, gets a negative sign. So I get minus 1 divided by square root of 4 times the 2 state. And the other ones don't change. So the operator does, the mathematical construction that I gave you for this operator does exactly what I told you that we want the operator to do. Namely, it flips the amplitude of the correct answer to a negative value, and then it doesn't change anything else. Oops. This amplitude got flipped down from 1 divided by square root of n to minus 1 divided by square root of n, and nothing else is changing. Okay, now let's move to the next part, which is the reversion around the mean. And again, what this operator does is that it simply inverts the state that we had around the mean value here. Now, of course, this can be represented, this outer product can also be represented as a matrix, and actually we can very quickly do that. So the outer product of an equal superposition, the S state is just, and again, as a reminder, the S state is just, oops, my boy scored a 4, 0 plus 1 plus 2 plus 3. So this outer product will give me 2 times. Okay, so there's a factor of 4 here, or 1 divided by square root of 4, and then it becomes squared. So I have 2 over 4 times a matrix with all the elements being 1. So we did this for the case with 2 states for a single qubit. Well, what I'm telling you is that it also extends. So I'm going to end up with a matrix with all ones. And then just minus the identity matrix, which is 1, 1, 1, 1, and zeros everywhere else. So what I end up with here is, let's see, so this is a 1/2. So I'm going to keep the 1/2 there, out here. And we're going to end up with -1 on the diagonals everywhere, and then just 1s everywhere else. And of course, there's a factor of 1/2 outside that I've kept there. So again, all this is another operator, or another matrix rather, that you multiply after you get the first operator. Now, of course, writing this down might be a little bit, it's gonna be a little cumbersome. So I'm gonna skip it in favor of the geometric argument, because what happens is that we have this U of S now, which I'm gonna call this U of S. U of S acting on the state, after we apply the Grover, or the oracle, the Grover oracle to it, to the equal superposition state. And now I can write this as U of S times U of W times acting on the S state. And I can just bundle these 2 operators up, multiply them, and just call them U of G, which is the Grover iteration, or the Grover operator. And that is what we have here when we say 1 Grover iteration.
Sorry, Amir,
Okay.
before you keep
Yes.
going, can you just clarify, remind us what we just did, the reversal about the mean, maybe said in words instead of numbers?
Yeah, absolutely. So again, this is what we've seen before, but these are the 2 components of the Grover algorithm. First, we use the oracle to flip the sign of the amplitude of the correct answer. And now that we flip the sign, we invert everything with respect to the mean. So that is I guess the cartoon that I have on the bottom right side of my screen. So since we flipped 1 amplitude down, since there's 1 negative value, then the average of all the amplitudes, it's going to be slightly less than what it was before. Now, when I flip things, when I flip all these amplitudes with respect to this mean line that I have over here, all the incorrect ones are above the mean line, so they go slightly down, whereas the correct answer is below the mean line. So it actually, and it's a decent bit below the mean line, so it goes up like that. And what we end up with after this is that the correct answer has a slightly higher probability of being measured than everything else. Now, if we repeat this enough times, this probability goes higher and higher and higher and higher.
Amir, quick question. Is the second operator that you're applying in that diagram on the right, is that UG or US?
Oh, that should be US, actually. That was changed. Yeah, thank you for clarifying that, actually. That is US. So that is this operator, this reversion, or reversing about the mean operator. Okay, with that, let's look at the the geometric argument for what these operators do, and then we can use that as a tool to, first of all, gain a better understanding for the algorithm itself, and analyze the runtime of it. So we first start with all of our states in an equal superposition. And now, of course, I'm generalizing this to n possible elements rather than just 4. So if I have n elements, then an equal superposition will have 1 divided by square root of n up front. And then it's going to be times 0 plus 1 plus ... every number, all the way to n minus 1. And the reason why it's n minus 1 instead of n is because we started from 0. So the total number of elements is actually n in this case. Now, what I'm telling you is that let's break down our world into 2 possibilities, or the state. The first option is the W state, the winner that we're looking for. So, and again, in this case, I'm assuming only one winner, but of course you can generalize this to multiple targets. So, okay, let's assume that W is the target, and then let's also assume that everything else is the junk that we're not looking for. So, and I'm going to call that this S prime state that you see here, and I'll explain the plot to the right in a moment. So S prime is going to have n minus 1 elements. So everything that is not W, I'm going to call it S1. And I can show that as a superposition in this case with n minus 1 elements of 0 plus 1 all the way to n minus 1, but now not including W. So therefore, this superposition has n minus 1 elements, because the original superposition of everything had n elements, which included W. Now, if I take W out, I have 1 less element. So that is just all these other amplitudes, really. And the reason why I'm making this distinction is because the oracle operator acts the same on all these states. So I can just, essentially bundle them together as one superposition. So using this tool, now I can rewrite S as 1 divided by square root of n times the W state. So this is what we've seen earlier when W was 2, plus, now I'm going to have 1 divided by square root of n, but it's going to be n minus 1 divided by, square root of n times this S prime state. Now, if you do the math, if you actually plug in the value, what we have for S prime, this 1 divided by square root of n minus 1 in the denominator over here will cancel this square root of square root of n minus 1 in the numerator here. And we end up with, you know, the original definition that we had for S. So this is the only distinction that I'm making, and it's actually a very powerful one, because now if you look at, you know, the new way that I've written the S state, first of all, it should look familiar because there are only two options, and it looks a heck of a lot like a qubit state. But, you know, to make that point further, the overlap of W with itself is equal to 1, and the overlap of S prime with itself is also equal to 1. But now the overlap of the W state with the S prime state, which I've defined up there, is equal to 0, since the S prime state here, so this state, does not include W as an element of the superposition. So if the math is a little bit cumbersome, don't worry about it. Let's just focus on the picture that I have on the right representing it. So by writing things this way, I can essentially put my W state on one axis, and since we stated that S prime is perpendicular, I can put S prime on another axis. And now the original superposition that we have falls somewhere in between. In fact, I can calculate what this angle theta over 2 is by simply looking at what is the projection of this S state, like this vector, on the y-axis, which in this case is a W state. And this projection is just simply the sine of you know, whatever this angle is, since we're assuming that all of our amplitudes are equal to the amplitude of the vector, the length of this vector is 1. So therefore, in this case, sine of theta divided by 2 is just equal to 1 divided by square root of n. And then, you know, using some of our trig functions, we can also say that theta, in this case, the angle, or, you know, or theta over 2 really, the angle that we have between the S vector here and the x-axis, which is defined as the S prime state, is just going to be equal to the inverse sine of 1 divided by square root of n. So again, let's think about this problem. Let's think about Grover search as a geometric problem. We start with this state's equal superposition, which has some overlap with the correct state. In this case, the starting overlap is going to be very small, in fact. And our goal is to move this as high up as possible, such that it eventually overlaps with the W state. And all the operations that we do, we want them to get it closer and closer and closer and closer to overlapping with the correct state. Now, of course, if in this case, if theta is small, then theta. Okay, so let me write this as this. So this is a property from geometry. But if theta is small, then theta over 2 is just going to be equal to 1 divided by square root of n. And let's not worry about that too much, but we'll see where it comes into play. Okay, so that is just starting everything from an equal superposition. And again, all we've done is that we've divided our problem into the correct answer, which we represent on the y-axis, and a superposition of all the incorrect answers, which we're representing on the x-axis. And all we're trying to do is, starting from an equal superposition, which is somewhere between the two axes, we're trying to get as close as possible to the y-axis, which is where the correct answer is. And then we measure, and then we're going to get the correct answer. And this is very similar to operating a qubit, because in that case, there are also only two possible scenarios, two possible outcomes, or two levels, 0 and 1. In this case, the possible outcomes are the winner state and everything else.
Quick question from the chat, Amir. Is there a reason why we chose it to be theta by 2 and not just theta?
So it's the same argument as for the qubit, actually. So in this case, if we would have had W on the North Pole and S prime on the South Pole, then it would have been theta. But since since we have them to be 90 degrees, then that's just theta over 2. It's convention, and it's not going to affect the overall runtime analysis that we're going to see by the end of this. We're still going to get O of square root of n.
Thanks.
Okay, so after we get the oracle, if you remember, I'm gonna again rewrite this. So what I said is that we can write our state, the superposition, as S is equal to 1 divided by square root of n times the W state plus, and this is just for normalization, just to get the normalization right. And then some square root of n minus 1 divided by square root of n times the S prime state. So we're much closer here in this case when we start to getting the wrong answer than the right answer, but that's fine. So after I apply this Grover operator, this Grover oracle operator here to the S state, all that happens is that the coefficient in front of the W state flips. So I get minus 1 divided by square root of n times the W state, and then nothing changes with the coefficient in front of the S prime state. And again, this is theta over 2. So nothing is changing here. Now, if I look at the sign of theta over 2, in this case, the sign of angle, what is it? Well, it's just this coefficient, right? So I get minus 1 divided by square root of n, which all it means is that, we have flipped our state. We have rotated our state, the S state, around the x-axis that we had by the same angle. So we started at an angle theta over 2 from the x-axis, and then we flipped to an angle minus theta over 2. That's all that's happened. So the angle, so essentially it's like an angle rotation. So angle, I'm going to call this, by the way, theta prime. Rotated from theta over 2 to minus theta over 2. That's all that's happened. Now, next step, after we apply this U of S operator, or reversion around the mean, what happens is that, okay, so this is where we were at before, right? We were at, and okay, this is again wrong, this should be theta. So we were at angle negative theta over 2. This was U of W, or the oracle operator acting on S. And now we're flipping things around the original superposition state here. So let's see. Okay, so we started from, this angle is theta over 2. We went down to minus theta over 2. So in total, the angle between this state after applying the oracle operator and the original superposition S state is theta. So we end up going up from negative theta over 2 to, an additional theta plus theta over 2. So, okay, so after applying U of S, we rotate around the S state, which of course in this case is just a line. Now, for the first iteration, we started, or we were at before applying this operator, we were at the angle minus theta over 2. Rather, actually, okay, for the first iteration u of s takes us from angle minus theta over 2 to, well, theta plus theta over 2. So now for the first overall, so that was just for the second operator. Now for the entire Grover cycle or iteration, for the entire we started again from theta over 2. Again, we were at this S state, and we ended up at theta over 2 plus theta. So now what I'm going to tell you is, and you can check this, is that after t being some number of iterations, theta of t is going to be equal to t plus 1/2 times this original theta that we started with. And again, this is just inverse, or 2 times inverse sine of 1 divided by square root of n. So what you can see is as we do more and more Grover iterations, the resulting state goes higher and higher, closer and closer to the W state. Okay, so let's use this tool to look at the runtime. So what I told you is that after t iterations, the probability of measuring the W state is, so it's going to be sine squared, because it's probability, so it's whatever amplitude that we had squared. And it's going to be whatever angle we ended up with. That is t plus 1/2 times the original theta. Now, when is the value, when is this probability optimal? Well, so it is optimal when the argument that we have inside the sine is equal to pi over 2, or 90 degrees, because that's when sine is 1. So optimal when t plus 1/2 times theta, the original theta, in the original angle between the superposition state and the correct answer, is equal to pi over 2. So based on this, now this is a simple geometry problem. And again, let's assume, based on what I've told you earlier, that theta is almost equal to 1 divided by 2 square root of n. Or sorry, it's 2 times square root of n. So based on this, t optimal, which is the total number of Grover iterations needed, is going to be almost equal to pi divided by 4 times square root of n. And this is O of square root of n, because pi divided by 4 is just a constant. So the takeaway message here really is that the optimal runtime of Grover search, the total number of Grover iterations that we have to apply, the total number of operators that we have to apply, is O of square root of n. And that is the quadratic speed up that we promised you. It's quadratically faster than classical search using the approach that we talked about. Now, again, that might have been a little bit too much math. So maybe let's cap things off with, going back to the Waldo example that we have and making the same geometric argument for that case. So what we've done is that we've divided all possibilities, i.e. Elements of superposition, to two possible sets. So the first one is, what we're looking for, the W that we say usually refers to the winner, but in this case, you could also refer to Waldo, and everything else that we're not looking for, which we're just calling them N. So that is all these other characters that we have. And we're placing on two different axes. And the idea is that for our quantum state, we want it to be as close as possible to this W axis, because once we measure, that gives us the probability of measuring, the correct answer. Now, if we imagine these two sets as vectors, they're going to be orthogonal because they have nothing in common. And the main reason for that is because Waldo is in one set and the other set doesn't contain Waldo. So therefore, the sets don't overlap at all. They have nothing in common. Now we can plot the vector that represents all the choices. And I guess in this case, we're calling it A for average, but it's generally the S state that we talked about, the equal superposition. And of course, that element initially does include Waldo, but it has all these other elements. So that vector includes Waldo, but it also has all these other elements. So it's going to be much closer in terms of the overlap to the N vector, or the vector that contains all the options that we're not looking for, than the one that has the option that we're looking for. And that is just because that's the average. Now, what we want to do is I'm going to apply these our Grover operations such that we get closer and closer and closer to the W state. Okay. So what the oracle does is that flips A, again, the initial superposition state around the N axis, or the X axis. So again, if I'm writing the quantum states, that's S, and that is U of W, or the oracle operator acting on S. And then, okay, so yeah, actually, no, that is the result that we get. Basically, if I'm rewriting the probabilities, if I draw the probability amplitudes, the probability amplitude of the incorrect options won't change, because again, the cosine here isn't any different, but now the sign is flipped. So, if this was, let's say, this distance, I'm going to call it X, or no, let's call it Y. Now this distance is minus Y. Whereas, the overlap, or what we have here on the X-axis, is the same. And of course, the graph explains what's happening intuitively. And now what we do is that we flip the new vector, the resulting vector. Again, this is U of W acting on the state S around the initial average, which is the S state. And what we end up with is U of S, U of W acting on the S state. And what you can see here intuitively is that now we're getting closer and closer to the W state. So, here, like, we went all the way around closer to the W state. And the more that we repeat this operation up to a certain point, in fact, the T optimal that we calculated, or the number of optimal iterations that we calculated, like, the closer and closer we're going to get to the target state that we're looking for. And again, that corresponds to looking back at it in the probability amplitude picture that we have. That corresponded to all the wrong probability amplitudes, the ones that we're not looking for going down, and then the correct probability amplitude going up. So now if we measure, there's a high probability of seeing the correct answer. And with that, I would like to wrap up the lecture. I'd be happy to answer more questions. But again, basically, the way that you can think about this, the takeaway message really from Grover's algorithm and these amplitude amplification algorithms is that we can come up with efficient ways to constructively interfere such that the correct answer, the amplitude of the correct answer increases and the amplitude of all the incorrect answers decreases. So yeah, I'd be happy to answer any questions now.
I can jump in with a few questions from the chat. So one question that came up a few times was, again, kind of going back to oracles. So is it the case that every algorithm has its own oracle, or are these oracles kind of common?
Yeah, so actually that's a good question. That is very much algorithm dependent. So there are algorithms that require oracles, but for example, a Shor's factoring algorithm does not need an oracle. So it definitely depends from algorithm to algorithm.
Okay, and then another question was, so in this Grover's algorithm, we know that when we apply the UW, the oracle, right, that gives us a negative sign. Why can't we just measure that? Like, why do we need to do the rest of the algorithm?
Great question, because okay, let's go back here to the negative sign, right? So these are probability amplitudes and not probabilities. Now, if I'm measuring the state here, I'm measuring probabilities, which are these amplitudes squared. Now, if I square 1 divided by square root of n, that is just 1 divided by n. And if I square minus 1 divided by square root of n, that is also 1 divided by square root of n. So just after applying the oracle operator, there's no difference in the probability or in the measurement probability of the correct answer. It is only after applying it multiple times and combined with this with the reversing around the mean that we see that the probability of measuring the correct answer will actually go higher and higher and higher and higher.
Okay, and then some people are asking, so as you keep on applying this, is what happens that the final state keeps getting closer to W, and then if you continue applying it after that, will it like go back, or what happens then?
That is an amazing question. That's 100% correct. So it's a rotation, right? I can effectively all the operations that we're doing are rotations, and we could over rotate actually if we apply it too many times. So yeah, so if we apply too much beyond the optimal point, it will actually decrease the probability.
And then kind of going back to when you were talking about the runtime or the complexity of Grover's, could you re-clarify where the relation you sine theta by 2 is 1 by square root of n, where does that come from?
Yeah, so the argument in front of sine squared, the sine squared, right? Because the sine squared is the overlap of, actually, let me even use the vector picture that we have. That might be a little easier to understand. It's just an overlap of A with W. That's just, the sine theta is a probability amplitude, and then the probability of measuring it is actually sine squared. Now, I think the other question is, where does this t plus 1/2 divided times this theta come from? And the argument that I gave wasn't here, is that after one iteration, we go from theta divided by 2, well, okay, 0 iteration, we're at theta divided by 2 angle. After one iteration, we're at theta divided by 2 plus theta angle. And if we continue this, we will see that it's going to be, the number of iterations plus 1/2 times the original theta that we started with.
Okay. And then people are asking, so does this mean that does it mean that you don't always get 100% probability of measuring the right result? Yeah.
So something that I mentioned, actually, this is a paper that I read last night as I was preparing for this lecture, is that there is a slight modification to the algorithm such that you could actually measure the correct answer with 100% probability after doing it. And the modification, in short, involves, not necessarily flipping this all the way, like not adding a negative, for the oracle, not doing a full-on -1 times, but rather a phase e to the I5. And then, basically they optimized for what this phase should be, so to end up with an optimal answer. I can share the paper on Discord if people are interested, but it involves a modification to the operator, and you could make it such that you get the correct answer with 100% probability. But overall, a lot of the quantum algorithms are probabilistic at the end of the day, and that is completely fine, because there are these class of classical probabilistic algorithms that outperform classical deterministic algorithms. And again, that's an active area of research, but there are, we do use those algorithms classically a lot. And again, if even if you get like 90% probability, we can just run the circuit, 100 times or 10 times even, and pick the highest outcome, and then that's going to be the correct answer.
Okay, and then I guess this is kind of a repeat of another question that we discussed a bit earlier. So suppose I'm someone who wants to use Grover's to search a database, and I figure out a way to make a quantum RAM to actually encode all of my database states into quantum states. How do I know what oracle to use? If to make the oracle, if I already kind of need to know which state to mark, then is there any point to using the algorithm in the first place?
Yeah, I mean, so definitely oracle construction is an active area of research, and it does depend on the problem you're trying to solve. But the one thing that I'll say is that a lot of the times, we know what the element that we're looking for is. We don't know what index it's attached to. Mm-hmm. So what you'll do is that you'll construct an oracle that behaves the way that we want it, basically shown over here, for that particular state and for nothing else. And then the state is the state that you're looking for, and you're trying to find the index of where that state is stored.
One analogy that Phil, one of our TAs, which I thought was really helpful, was it's kind of like if you had to find a needle in a haystack, your oracle would be a big magnet, right? Because you know that the magnet it's just gonna attract the needle. It's gonna make the needle behave differently than the rest of the haystack.
Yeah, and actually to that point, Grover, Love Grover, the person who came up with Grover's search algorithm, the paper about Grover's algorithm is titled that. It's called "Finding a Needle in a Haystack." So yeah, that analogy works very well. But again, the one slide that I want to go back to for that is, the slide that we had on, if I don't accidentally zoom in constantly, the slide that we had on here is that, we know what we're looking for, we know the properties, we just don't know where it is.
All right, with those fabulous analogies, how about we wrap up there, Amir? Any closing thoughts?
Yeah, so these quantum algorithms are definitely more complex than the ideas that we've seen earlier in the course. But I think, what we should really what we should really aim to get out of them, if not the algorithm specifics is, the quantum algorithmic thinking, mainly the tools that are at our disposal. In this case, we talked about amplitude amplification and how we can do it specifically for search. But of course, this is a technique that can extend well beyond quantum search and apply to other problems as well. So yeah, again, like the TA team would be more than happy to answer a question. We have an amazing team. But the biggest takeaway message is that amplitude amplification, and again, in words, increasing the amplitude of the correct answer and decreasing the amplitude of all the incorrect answers using interference, is one of the tools in our quantum toolbox to gain a quantum speed up.
Perfect. All right, we will see everyone in lab this week, and then enjoy your spring break. All right, bye-bye.